Hi, my name is Jessica Brown, and I'll be presenting today on the effects of pertubed depth sensors in autonomous ground vehicles. This is a 4-year project between Michigan Technological University, the University of Missouri, and the U.S. Army ERDC. I personally am on the Michigan Tech team. So, as an introduction, we are investigating the effects of pertubed LiDAR measurements on autonomy functions. We're exploring 6 different models, and from there developing behavior-based autonomy for obstacle avoidance, waypoint navigation, and path planning. We'll be demonstrating autonomy functions in the presence of perturbation models. So for this, we are using AirSim and the Unreal Engine. This will provide a physics-based simulation of UAVs and vehicles in realistic environments with the autonomy sensor models that we need, like LiDAR, RGB sensors, etc. So here to the left, we can see a more realistic looking environment where it has a city landscape and has a lot of different objects, like from trees to street lamps to other cars, and it simulates this car right here driving. This will be used in our more advanced simulations and experiments later on, but we are currently in the very beginning of this 4-year project. So we are just starting with simple experiments where we've created an environment with a couple objects, block-like objects around, and we have our starting position that our robot starts at, and then it needs to reach the goal position, which is around this block. So it does have to make a path. Going into the different models we have, there are 6 of them, and they are based on simple additions or alterations to LiDAR point clouds, and they are implemented with middleman and ROS nodes. So our first model is snow. And so here to the left, we can see when there is no model. And this grid right here is our vehicle. And then all these lines are the objects that it detects. And so here with snow, we have a simulation of spurious sensor measurements. So kind of just things are detected all throughout, kind of like if it was snowing, this robot would be detecting snow everywhere. And so as we can see, it's just very small points scattered throughout. And then we go to noise, which simulates various qualities of sensor measurements. And so this just exaggerates basically the detection of the different objects around. And so here we can see what it looks like when there's no perturbation. But then with one, it's a lot fuzzier and the object itself, like the detection of it, is thicker. We also have local noise, which is degraded quality of sensor measurements at a specific scan angle. So right here you can see only a specific section has noise added to it. The rest is normal, just this one specific section. And then we have clouds, which simulates local noisy clouds of sensor measurements. Right here we have this small cloud of points. And in these examples or experiments that we run, this point cloud does not move. It moves with the vehicle, but it does not move around the vehicle. It will stay in this exact location in reference to the vehicle. And then we have blobs, which do move around and disappear and reappear sporadically. So as you can see, there are different sizes, and this is just a still image. But when the vehicle is actually moving, an experiment is happening, these are disappearing and reappearing all over the area that the vehicle is sensing. And lastly, we have local blanks, which is just missing sensor measurements. So you can see this object is being detected right here, but the whole middle section is just not being detected. It does not see anything there at all, even though there is a wall or an object. So now we're going to be diving into the autonomy algorithm that we used for this. So we're doing our robot path planning, and it's based on 3 different behaviors. We have obstacle avoidance, so we don't want to run into the actual objects that are in our environment. We have goal seeking. We want our robot to be able to reach a certain point that we want it to. And then also we want to avoid large turns because those are very unrealistic and not actually what occurs in the real world. We want our robot to be able to make sharp turns, no different than it'd be like turning a corner on a street. These behaviors are aggregated into a cost function that determines the direction of motion, and the dependent variable is the direction of travel. So looking more specifically into this algorithm, we have our 3 different sections that are added together: our obstacle avoidance, goal seeking, and a limit on big turns. So r theta is the distance to the nearest obstacle at angle theta. Theta with an asterisk is the direction towards the goal. Theta t is the current direction of travel, and theta b is the limit on turn angle at a given time step. Now looking into our experiment. What we did is we had our robot placed at the start position, and we just ran it and had it travel to this goal position. It would move in a direction that minimized the cost function at 1 meter per second. And then when the robot reaches the goal, the simulation ends and the path length is computed for each run. And that is how we determined how obscured the path was based on each perturbation model. So for each of the 6 models, the experiment was run 10 times. And so looking at the results for when we use snow, it shows the degradation of the path. Oh my gosh, my apologies. There we go. My apologies on that. So when we added snow and ran it 10 times, it showed how the path degraded as the drone had to navigate around the just random sporadic little objects it detected in the sensor measurements. And so you can see here to the left is when there was no perturbation. Every single time it made a clean path just around the object. Here, when there's snow, you can tell there's a lot of variation in the path it took, having to kind of avoid the snow that it noticed in the path. And then with blobs and clouds, they caused the drone to see objects that were not there, significantly altering the path to the goal. So you can read here with, my apologies, I think my computer is acting up. There we go. So with blobs, we have, since they were just appearing randomly all over the place, we can see that it caused a lot of disturbance right here, especially when you're trying to make this turn. You can see where the robot would almost have to back up and make small turns to navigate around these randomly appearing blobs. And also with the clouds perturbation, it's a little different because that one cloud point stayed in the same position. So you can see the robot was not affected by that until it hit this final section right here. And instead of being able to make this diagonal right here, the cloud was in the way. And so it had to go farther along and wrap around to get to the goal point. And then looking at the noise perturbations, it did not make too much of a difference simply because the robot just basically gave the objects a wider border because it noticed the objects from further away. So it more or less just made the robot think the objects were bigger and kind of give it a bigger barrier when traveling around it. And then finally, we have the local blanks perturbation, which just caused the drone to miss seeing the obstacle until it was very close. And so the object just went straight, the robot went straight into the object. And then once it realized there wasn't actually an object there, it then kind of followed the wall very closely and wrapped around until it reached the point. Looking at the results, when we see there's no perturbation, the experiment ran and the path length was about 90 meters for every single path. And then with snow, there was slight variation, but blobs was by far the perturbation that caused the most deferral from the usual path. Since these blobs appeared randomly throughout the different lengths of the runs, very widely, but a few of the runs are as long as 260 plus meters, where without any model, it was only 90 meters. So that's a huge change. And the clouds also caused the paths to be longer, and both the clouds and blobs did this because they caused the drone to see obstacles that weren't actually there. The noise models were the least effective because all they did is make the objects seem bigger than they actually were and just made the robot give them a wider path around. So in summary, we've developed and executed an experiment to behavior to see the simple autonomy in the face of LiDAR perturbations. The results provided good connections between the types of perturbations that were most disruptive to the autonomy and taught us that ones like clouds and blobs, where it makes it seem like there is an object that isn't actually there, are the most effective. Our future experiments will explore the robust autonomy approaches for mitigating these effects of sensor perturbations, and we will for sure focus more on ones like clouds and blobs that were shown to be most effective in this experiment. And as we get farther along in our experiments, we will start using more complex environments like the city model that was shown earlier. And I'm excited to see where that research takes us. I also have another link on my page here for some other research that was done regarding how these models would affect object detection with YOLO V3. We decided to not pursue this and instead focus on these LiDAR perturbations with following paths. But there will be another presentation showing my initial research into object detection and how things like noise can affect it. Thank you.